So welcome everyone to the Anonymous and Credentials and Blueprint session. We will have two talks today. The first one is on updatable privacy-preserving blueprints, and Mikhail Volkov will give the talk.
Okay, the mic works, right? Hello, everyone. Yeah, this work is called Updatable Privacy-Preserving Blueprints. I'm Mikhail Volkov, and this is a joint work with Bernardo David, Felix Angel Montoro, Frederic Markov Kohlweis, and Alan Epanin. So in this work, we start with the problem of regulation compliance and data scanning. So assume that a user owns a certain secret data X that they don't want to reveal. This is the data that they own on the client side. At the same time, there is a regulator who wants to check that this data is legal according to certain predicate P. So if the predicate is 0, the data is legal and otherwise is legal. Assume also the regulator defines the predicate, has some secret ZI, which kind of, for example, has a bad content kind of text, so to say. So if the content is in this database Z, it is child sex abuse material or something. The regulator wants to check that, but it doesn't want to reveal data to the users. It's kind of like two-party computation. A regulator wants to get the result, but no one wants to give away the data. Simple solution, the user can just send this data over to the regulator can check that. Obviously, that works on private for the user. You can use MPC. MPC is usually more interaction, however, that one we're going to present in this talk. So like speeds or something. And you can use also client-side scanning, which is quite a common approach these days. So you can just force the client application like WhatsApp to scan your data and then report to the regulator if that is real or not, illegal or not, in the native computations or SGX. This undermines users' privacy, and also this is prone to leaking the Z from the regulator side. I highly recommend reading this paper, Bugs in Our Pockets, if you're any worried about the chat control regulation of the European Union that they tried to pass for like 5 years and failing. So it's a very reasonable and recent problem. The work by Kohlweis, Lasenska, and Anyen, Asiacrypt 23, solves this problem, or provides a solution for this problem. That is a privacy-preserving blueprint. So a blueprint is, in the common sense of the word, is something that you can use to build something else, so like a recipe, So the blueprint in this work is this blue envelope. Yeah, you can't see it anyway. It's a blue envelope that contains the secret of the regulator in a certain way, in an encrypted way. So this secret is committed and it cannot be changed on the fly. So the user has a secret X, and the user can transform this blueprint into what is called the escrow. And the escrow kind of contains the result of the predicate evaluation, which is sent back to the regulator, and regulator can check if the escrow verifies and if it decrypts to the correct value. So in this way, regulator learns the predicate, but it doesn't know the secret X, and the user is able to create the escrow without revealing X, and it doesn't also see the regulator's secret. This work has a follow-up, which will be presented by Scott in the following talk in this session. In this particular paper, we asked the question of, can we make construction updatable? So can we actually allow users to update the secret in their blueprints? So we start with the, what's called like counterclockwise. So the regulator creates the predicate, it has a setup phase, and then it sends this blueprint envelope to the bottom user. The bottom user adds the value x1 to the secret, and then the second user adds the value x2, and the third person has the value x3, and then the escrow is created. And then the regulator can verify whether the escrow is true or not, whether it relates to the predicate or not, on the sum of the values xi. So there is a sum of xi there, not just one xi. Which privacy properties do we want to get here? So the user knows their own update value, so the user knows what they want to add to the updatable blueprint, but they should not see the regulator secret, they should not see secrets of the previous step or other users, and they should not know anything about the predicate. So you get something that you can evaluate the predicate on, you update it, and then you send it over. That's it. This construction has a lot of applications and interesting corner case, interesting scenarios that it can be used in. So one of the prominent one that we kind of show as an example quite often is, imagine every single update value is an increment of your rating. And the predicate here is the predicate that we'll be using quite often. It's called the range predicate. So the predicate is true on the range from t to t plus delta. So if you're in this range, you're illegal. And if you're outside this range, you're kind of legal. Okay. And assume that we have kind of banks tracking your rating or suspiciousness score. So credit score type of example. So you have a value of your rating, and it moves by delta at most increments, so plus minus. If it gets to the dangerous predicate range from t to t plus delta, the regulator will learn about your rating. But no one knows about the rating before that. So in this example, the regulator forces banks to keep you at rating, and banks track your rating, but no one actually knows what your suspiciousness score is. So even banks don't know. Banks can like say, oh, it's like +10 or -10, depending on transaction suspiciousness. And in the end, regulator can like learn at some point that you're too suspicious. You can also do primitive voting with this construction, where you have like every X is just 1, so you can either vote or not vote. And in the extensions of our paper they provide provide in our paper, you can also evaluate much more powerful predicates, such as this equivalent proximity testing predicate, where a regulator can kind of learn if you're in a certain vicinity of a 2D point, which can be used for COVID proximity testing. If you want to talk about that, come after the talk. So the contributions of these papers, they provide the new notion called updatable blueprints, which is kind of an updatable variant of privacy-preserving blueprints. The instantiation that we provide is for range predicates, so the one that I showed before. Very importantly, it showcases the primitive called updatable algebraic zero-knowledge proofs, which I will explain in the main part of the presentation. And this is extendable to a large class of predicates. So there is no limitation for range predicates. It's just more of a test subject. Okay, so getting back into the main construction. So the syntax of the construction is as follows. Regulator has a threshold, it's a secret. It commits the secret, it creates a secret key, public key of the regulator, and then it creates the hint. So importantly, I will not use the word blueprint almost in this presentation. Technically, hint is the technical term for blueprint. So this hint is something that users kind of hint each other to create the polynomial evaluation. So there is this original hint that is created by the regulator. It is sent to the users. Every user can verify the hint and update the hint with their secret value. The hint is something like containing the monomials if you want to build some intuitions. A hint is something that contains monomials in 2 variables that you can evaluate stuff from. And many users can transmit these hints to each other, update the value, and so on. When they want to, users can evaluate these hints into what we call an escrow. So they create an escrow. And the escrow contains the evaluation of this polynomial in a certain way. And the escrow can be sent to the regulator, and the regulator will check the escrow, decrypt the escrow, and it will learn the result of the predicate without learning the secret of the user. So there is only like minimal interaction here. It's no like quadratic interaction or anything. Okay, this is the main construction idea in the honest case. It's not very complicated. The initial hints that the regulator creates are the encryptions to the public key of the regulator, regular LGML encryptions. There is only one public key here, it's a regulated public key. And what we encrypt is the polynomial, quote unquote. By that I mean it's kind of like monomials that can be used to evaluate this polynomial. Originally, there is no user secrets. Originally, the secret X is equal to 0. Every single user now gets these hints and updates them using their private secret X iota, gets a new set of hints. And finally, when the user wants to escrow evaluate the predicate, it can combine this monomials in a specific way in the exponent and also add this beta randomizer on top. So this has a property that if the polynomial is 0, the beta times polynomial will be also 0. So if the polynomial is 0, the regulator will know that it is so. If the polynomial is not 0, then the regulator will get a randomly uniformly distributed value, so that it will not know the value of the polynomial, but it will know that it doesn't hold. Which is exactly what we want. Getting more into technical details, I already mentioned threshold predicate, so it's the one that is evaluated from T to T plus D. Importantly for our efficient construction, we have to represent it efficiently using this kind of Stirling coefficient representation. So if you look at the polynomial, there is a public coefficient called UI, such that this formula holds true. So you can evaluate your polynomial. You can evaluate your polynomial not by evaluating the product, but by evaluating the sum over the terms x minus t. So just for this type of polynomial, we can do that. Okay. This is very effective because essentially we can evaluate things in linear time and not quadratic time. I will explain in a second. So the hints, or the blueprint, it's an LGML encryption to the regulator of the x minus t to the power of I. So according to this formula. So we just encrypt x minus t to the power of I. So 2 secrets. When the regulator generates the key, originally it sets the x to 0, and it should prove that it is so. Using the previous formula, if you have now LGML ciphertext, you can easily evaluate the polynomial p of x in the exponent. You just need to, take your LGML ciphertext and exponentiate them to the Stirling coefficients, and you get this formula in the exponent, which is exactly equal to evaluation of p of t of x. So yeah, from hints, you got evaluation of the polynomial. That's cool. If you want to have an escrow now, so you need to additionally like slap the randomizer beta on top, and you get the encryption of b beta times p of t of x. Okay, that was easy. Now, the updating hints part is a bit more complicated. So remember, hints contain like these x minus t monomials, and we want to move from x minus t to x minus t plus y. So instead of containing the secret x, we want to contain the secret x plus y. By regular binomial expansion formula, you can see that the new updated hints are just old hints, x minus t, of lower powers j, times this coefficient, which is just a binomial coefficients multiplied by the secret of the user. So y is the update value that we want to add. This means that if you have hints a and b, and look at the b formula, so you can take this hints b and you can apply the top formula in the exponent. So you just exponentiate your hints, and you get the hints for x minus t plus y. That's very easy. Caveat, I didn't show the formula for a for simplicity reasons, but it should be the same formula for the randomizers to be consistent. And note that you don't need to know the previous secret. So if you have encodings of a and b, you don't know what's the secret inside. You don't know x, you don't know t, but you can still update it to x plus y minus t. Yeah, honest construction is as follows. You get some hints, you update them by formula below, you send them over. If a regulator wants you to report whether this is legal or not, you just evaluate this using Stirling coefficients and extra beta, so you get the beta times polynomial. Okay, that is just the basic kind of functionality case, so we don't have soundness and don't have privacy. So for privacy, the biggest problem I would say that we will need for soundness purposes to send these hints to the regulator so the regulator can check if these hints are correctly constructed. And the hints are just LGML ciphertext, so we need to blind them, because otherwise adversary will be able to decode them and recover the individual monomials, which we don't want. We only want adversary to regulator to learn the predicate value, not the individual values of x and t. Now, the much more interesting part is the soundness. So we have 4 different proofs in the system to make sure that every step is executed correctly, both by the user and the regulator. So 3 of them, trace proof, key proof, and escrow proof, they kind of prove different parts of the system that, there is a history of updates. I will explain what history is in a bit. The key generation is correct, and the escrow procedure is correct. And this is all you can do with Schnorr, with Sigma protocols. And we use standard Schnorr Sigma protocols with extra LGML ciphertext for straight line simulation extractability. The consistency one is funny, because if you want to prove that your monomials inside the x minus t, if you want to prove they're all consistent, they're all with respect to the same x and t. So, you don't have for the power 5 to the power 7, you don't have different witnesses. If you want to make sure they're all about the same witness, you have to prove it. And if you do it with Schnorr, you would incur a linear cost every update you do. So this is because, if you just have Schnorr and you want to prove that, these ciphertexts and these ciphertexts are correctly, the right one is an update of the left one with respect to some secret value that I know. If you do a Schnorr proof like that, to verify that your hints are correct, you would need to verify this proof and the previous update proof and the previous update proof. So you would need to verify a linear number of Schnorr proofs. Now, that is really expensive, and because the hints are quite big in degrees. So instead of that, we use updatable NISX that allow you to always update the previous proof and not aggregate them over the way. What are updatable NISX? Well, if you have instance and witness in the relation, you can always update them, quite often you can update them to a different instance and witness in the same relation. You can think about it like the simple relation is ciphertext, knowledge of the preimage of the LGML. I don't know. So you say there's a message, a witness, and the randomness, a witness, and the encryption, the ciphertext is the instance. So you can homomorphically add something to the instance, and this will be a new instance, and you can also change the witness correspondingly. So there are lots of language transformations for languages. This is kind of obvious. Now, when you create a proof for a statement X, the more interesting part is that some proof systems allow you to transform the proof pi into a different proof pi prime that holds for this X prime. Importantly, the NISX update function doesn't know anything about the witness. So you can have a statement about your witness and instance, and you can transform the proof into a different proof, and you don't know anything about the previous witness. So you can kind of manipulate on secretly hidden values. So you shouldn't probably be very surprised about this, because a lot of recursive snarks do exactly that. So this middle part of the diagram, which I unfortunately cannot delve into for a long time, is a lot of the production level industry snarks, Plonk, Sonic, whatever, snarks. This is what we use in O1 Labs. This is what everyone uses. So in practice, this is modelable only via recursion. So you don't really you cannot really change them directly algebraically. So what we're interested here is this bottom corner. All the random oracle snarks, all the random oracle nizzics are not moldable because of Fiat-Shamir transformation. There's negative results about that. So what we're kind of curious is like grosse high and like small CRS-based nizzics that are simple enough so you can like directly modify them. So luckily enough, there is this proof system called CH20 by Cotu, Geoffroy, and Dominic Hartmann, 2020 crypto. Yes, this is kind of like a Sigma protocol for the algebraic language. So matrix time witness equal to witness. It's very similar to discrete logarithm relation. So it's kind of like a Sigma protocol, but done in pairings. So you have a challenge in the CRS. When you prove the commitment is in the first group, the response is in the second group, and verification is in pairings. That's just literally Sigma protocol in pairings, right? But the cool part is that the CH20 is actually updatable because there is no hash inside. So if you have a proof for a statement, you can transform it to a different proof for a different statement, where this think matrices is what you define how you transform the instance and the witness. The important caveat is that at least what we were like, when we were looking at it, we discovered that not all the transformations that are language transformations are valid for the proof. So there is this extra notion called blinding compatible transformation that define which transformation can actually work with the proof. Fortunately, I don't have time to explain blinding compatibility, but it's a very interesting problem to learn whether all the language transformations can be transformed into proof transformations. So now we have the standard diagram I showed you already 5 times. You have hints, you update them, you do the escrow, and you just slap the proof on top. So whenever you update your hints, you also update the proof. And so you don't have any linearly accumulated proof here, technically speaking. You just update the proof all the time and you pass it over. It's very convenient. This is just the language for the proof that we use. It's very concise. One small detail is that we also have this notion of history, because so far what I explained to you, the construction doesn't really have any way to reason like about the update number 5, update number 7, or how they are ordered even. So we have this small, very concise functionality called like a chain of update receipts called tags. So every tag is just a small snore proof, a small commitment, and they are referred to each other. So using this, you can in a very light way order all the proof updates if you need that. So you can put them, they're all hiding, you can put them on the blockchain and basically have a committed history of updates, and every single proof is like anonymous receipt. Security properties in construction are soundness, like binding and different types of hiding. So all the things are in some degree hiding. Soundness, perhaps very interesting for soundness, is that the CH20 proof is not knowledge sound. So if you want to extract from that, you cannot. So instead we extract from this straight line extractable history proofs, the regular schnorrs, and we use that data for proving the system sound. Yeah, hiding is generally like zero knowledge stuff. And all the properties are proved in the under game-based definitions. There is no simulation there in one notion. All under standard assumptions. The Nizek assumption is variant of kernel MDH, which is kind of relevant to standard discrete logarithm and bilinear groups. Size-wise, the hints and escrows are linear in the size of the polynomial. So this threshold polynomial that I showed to you, the d is its degree. So hints and escrow are linear in that. And I doubt you can really avoid that, because to evaluate the polynomial, you need to have d values, technically speaking. So in trench theoretical, I think this is quite good. In terms of performance and time complexity, all of the algorithms are linear or like sublinear, except for the update, which is quadratic. And the problem here is that to update the hints, every hint contains a monomial, and every monomial needs to be updated by a linear formula. So you have linear number of linear updates. This potentially might be doable in d log d. I don't know. This is a good question for future work. In practice, we evaluated this on a regular, fairly accessible machine, and the realistic degree of polynomials that we can handle is about like several hundreds. So you can see that most algorithms kind of fall within 1 to 10 second time frame, and the most expensive one is this quadratic update that is kind of a bottleneck. It's also very important to note to mention that even though the construction is made for the range predicates, which are kind of very simple and limited, it is clearly possible to generalize it towards different types of predicate. So instead of doing these fancy hints with Stirling coefficients, you can just do quadratic number of hints, so x to the I, t to the j. You can also generalize multivariate polynomials by running the construction in parallel for different variables separately. And instead of returning just the predicate value, you can return this kind of binary condition. So if the predicate is true, return P2. This is useful, for example, if adversary wants to check that if you're in the range, return me your secret key. So you can kind of do this computation where adversary learns more if you're illegal. Open questions are how powerful is this primitive with the construction? So the extensions that we show, we didn't provide rigorous proofs for. So the main construction focuses on the range predicate, but it's interesting whether this can be applied to different examples, like I showed you with the COVID tracking and so on. And there is a question of how powerful the CH20 proof is. I'm quite convinced this is understated and very useful because a lot of algebraic cryptography can be quite updatable. And in terms of performance, I'm quite curious, can we decrease the size of the blueprint? And can we also support bigger size D beyond several hundreds? The following work by Scott will actually answer the first question positively for non-updatable case. In a summary, we present a new primitive called updatable blueprints. We realize it efficiently using the updatable algebraic musics, which is quite a cool technique. And there are quite a few interesting extensions that allow more powerful predicates in applications. Thank you.
Thank you for the nice talk. Do we have any questions from the audience?
That's a great talk. I have a small question. You were mentioning about applications, about interval membership, where a regulator doesn't know the precise value which is being compared against the interval. Does it work the same way on the other side, as in the client doesn't know what interval he is comparing its value against?
If I answer your question correctly, the answer would be that indeed the main property here is that the client also doesn't know the threshold. So this is that
the
your question?
Entire interval it doesn't know. Like
No,
which
so,
interval is checking against?
So the regulator hides its secrets, so the regulator hides certain variables and the user hides certain variables. So the user doesn't know the predicate and the regulator doesn't know the user's secret. So it's kind of like each party hides some secret. Does that answer your question? Or? Yes. Thank you, sir.
I also had a quick question. So you mentioned some extensions for multivariate polynomials and so how does the public parameter size scale with these extensions?
Terribly.
I
would assume. Let me think about that. So there is no these extensions are defined at least in the paper in a very conceptual way. So we just say that this is possible in theory. In practice, you incur, at least for the first extension, you move from the linear number of hints to quadratic number of hints. So I think this makes some quite a few algorithms quadratic, which kind of limits the top level of the degree D. It might be still possible and effective for the lower degree D. For example, for this Euclidean predicate, the degree is like 2, so it might be perfectly fine for that. But yeah, I think some algorithms become quadratic. For multivariate, I cannot give you an exact asymptotic, but I would assume at least quadratic, definitely quadratic. For several algorithms, maybe a bit worse, because you need to run several pairs of algorithms at the same time. It's an interesting open question.
Thanks.
Thank you. Okay.
Then let's thank the speaker again. So the next talk is about delegatable anonymous credentials from mercurial signatures with stronger privacy. And this is a joint work of Scott Griffey, Anna Lisanskaya, Amit Mir, Octavio Perez-Kempner, and Daniel Slamanik. And Scott would give it a talk.
Okay, thank you for the introduction. This is my talk, delegatable anonymous credentials from mercurial signatures with stronger privacy. Joint work with Anna, Omid, Octavio, and Daniel. Just as an overview of this talk, first we're going to go over what mercurial signatures are, Then we're going to talk about the literature behind mercurial signatures a little bit. Then we're going to look at an open problem with one of the existing mercurial signature constructions. And then we're going to go over our contribution, which is fixing this open problem with mercurial signature construction. And yeah, this actually has nothing to do with blueprints, sorry. But yeah, thank you for citing me, yeah. So what are mercurial signatures? At a base level, they're signatures, right? So we have a public key, and we can sign messages to get signatures, which verify it. But kind of the cool thing about mercurial signatures is that after you've signed this message, you can go and randomize the key along with the message, and then update that signature so that it verifies with the newly randomized key and message. Why is this useful? Like, it's kind of weird because now we have this PK prime that like the verifier might not trust. It's just a random public key. Well, it's actually really useful for delegatable anonymous credentials. So what are delegatable anonymous credentials? So in this example, let's say we have a government that wants to issue like national IDs to citizens in a country. But it doesn't want to interact with each citizen individually. So what it's going to do is delegate its issuing power to like local regions of the country. And then those regions are going to go sign all of the individual citizens in their own regions, just to make things more efficient. And they're anonymous, so when one of the citizens wants to show that they have a national ID, they can randomize everything so that they hide their identity and which region they're from. And so how do we construct this from mercurial signatures is we sign a credential chain of keys. So the government is going to sign the public key of the local region, and then that local region is going to sign the public key of the citizen. And then with mercurial signatures, we're able to randomize the key of the region, which I'll call the intermediate issuer, along with the key of the citizen, but we're able to keep the root key the same, the key of the government. So when you show this randomized credential chain, the verifier knows the key of the government, so they'll be able to verify that the end user does have a signature, a national ID. And because they're mercurial signatures, once you update them, they verify and everything works. So just a little bit of background on mercurial signatures. Starting in this work, FHS 19, they constructed these signatures with randomizable messages. And then BHKS 18 introduced randomization for public keys. And then mercurial signatures, starting with CL19, Kreutzing-Wostonskaya, they kind of combine these notions of message randomization and key randomization into one signature. And there's been a lot of other work, including at this conference, on mercurial signatures. And delegatable anonymous credentials are kind of developed parallel, starting in 2009 with this Belinky et al. 09, BCC 09. And they created their construction with Grasa high proofs. So yeah, started in 09. CL19 used mercurial signatures instead of Grasa high proofs to create delegatable anonymous credentials. And we're going to be focusing on the CL19 construction in this talk. That's where the open problem lies. How does delegatable anonymous credential anonymity work in CL19? Well, we have this credential chain, like I showed earlier, with the government issuing to a region, issuing to a citizen. And they're going to randomize and show their credential. And they're going to remain anonymous, meaning the verifier can't tell which citizen or which region issued this credential, as long as the intermediate issuer is honest. And it actually turns out with their construction, if you strengthen their definition, it's actually susceptible to an attack, where if the intermediate issuer and the verifier collude, they can actually take a showing of credential and determine which region issued that credential. So our contribution is to close this gap and create a mercurial signature scheme such that when you create delegatable anonymous credentials out of it, you get this stronger definition of anonymity where the intermediate issuer doesn't have to be honest. So just as an overview of our contributions, we create this mercurial signature scheme with stronger privacy, and it's going to use a trusted setup, actually. So that's the catch. We have a structured CRS that makes this all possible. And besides that, we use bilinear pairings, and our proofs are in the generic group model, which is the same model that CL19 used. And then further, we create DAC from this signature scheme, and then we add a few more things. We add revocation, which is an interesting thing that you can do with DAC from mercurial signatures. DAC is delegatable anonymous credentials. And then to kind of make the trusted setup more appealing, we allow for our structured CRS to be updated non-interactively. Cool. So now I'm going to try and explain our definition and construction, starting with a simple formalization of mercurial signatures. So as I said before, at a base level, they're signatures. So we have key generation, signing, and verifying. And it all works just like you'd expect with unforgeability and everything. But then they have this randomization property. What happens is it's a two-part step. So if you have a verifying tuple of a key, message, and signature, you can update the key with what we call a conversion factor. And then if you take that same conversion factor and update the signature, it ends up verifying. And if you randomly sample the conversion factor, now no one can guess how you updated it, and it gives you privacy properties. Yeah, and so I've highlighted the conversion factor here so you can see. And so what do we mean by privacy in this setting? Well, CL19 came up with this definition called public key class hiding. And it's a game played between challenger and adversary where the challenger is going to sample two keys, and then they're going to flip a bit, and then and sample a conversion factor, and then randomize one of those keys with the conversion factor. And then they're going to send over the first key along with the randomized key, PKB prime, and then the adversary is going to choose a message for them to sign, and then they're going to sign it with their own challenge. They're going to sign it with both keys and then pick one of those signatures to randomize and then send it back over along with a signature from the first key. And basically, the adversary's job is to determine which key this randomized key, PKB prime, was randomized from. Yep. So hopefully that makes sense. And so how do they construct this? Well, they're going to use bilinear pairings. And usually the generators are G, but I'm using P and P hat for the generators of the first and second source group of bilinear pairings, just notation. And so in CL19, when you generate a key, you're going to sample a vector of scalars, x1 and x2, as the secret key. And then the public key is going to be the generator of the second source group raised to the power of that secret key, x1 and x2. And then when you randomize it, you're going to sample a random conversion factor and just exponentiate both elements of the key to that value. And then they also have all these other functions that ensure correctness and verification and privacy that I'm probably not going to talk about in this talk. In this paper, we want to strengthen their definition of public key class citing. So we come up with this adversarial public key class citing. So I'll show this definition and then show why their construction doesn't meet this definition. So in this game, the challenger is going to sample just one key, and then the adversary is going to choose the other key in the game. That's kind of the difference, is that in the original public key class citing, the challenger chooses both keys. In this game, the adversary gets to choose the second one. So the adversary is going to choose this key and also sign a message kind of to help the challenger out. And then the challenger is going to sign that same message with their own key and then sample a random bit and randomize one of the two keys and then send it back over along with the randomized signature. And then again, the adversary is tasked with determining if this randomized key, PKB prime, is a randomization of the challenger's key or if it's a randomization of the adversary's key. And yeah, looking at this, maybe you can figure out why this helps us get a stronger privacy notion for DAC. I'm not going to have slides on that, though. Okay, so why does CL19 not satisfy this stronger definition? Well, let's go through the game and along with an attack. So in our adversarial public key class citing definition, the challenger sends over this PK1, and then the adversary gets to choose the public key. So they sample the secret key themselves, so they know the secret key. And then they send it back over along with a signature they created. And then the challenger is going to randomize one of the keys and send back over the PKB prime. And it turns out that the adversary, in this case with CL19, can use their secret key basically to just test which key that PKB prime is a randomization of. If in the case of B2, if they raise the first element of the public key to the power of function of the secret key, it'll equal the second element. But if it's the challenger's public key, this won't hold. And just to kind of explain the math a little more, if you look at the structure of a key, after randomization, the discrete log between the two elements remains the same. So like you're just exponentiating both elements by one scalar, the conversion factor. So that doesn't actually change the discrete log. But in the case of an independently sampled key, the discrete log is just going to be different. So that's how the distinguishing attack works. So now just a little bit of intuition for how our construction in this paper solves this open problem and realizes this stronger definition of public key class citing. So what we're going to do is create a structured CRS, and we're going to sample two scalars and then reveal these bases, B1 and B2, as public parameters for people to use, which these bases are just the generator of the second source group raised to the power of B1 and B2. And then when signers create their keys based on these public parameters, they're still going to sample their secret key the same way, but now instead of using the default generator of the second group, they're going to use these new bases that we defined for them, B1 and B2. And if they do it this way, now after the public key has been randomized, this is old slides. After the public key has been randomized, it turns out that when you try this recognition attack, when you raise the first element of the randomized key to this function of the secret key, it's going to have this scalar B1 in it, while the second element is going to have this scalar B2 in it. So the recognition attack isn't going to work. And actually, distinguishing it reduces to the DDH assumption. So cool. I hope we all understand that. I think I have a little bit of time to explain these slides. I just wanted to explain that like it's actually not that simple. When we look at the full construction, it turns out we're trying to sign messages which are vectors of the first source group. And to do that, we're going to exponentiate each element of the message, creating a signature with 3 elements, z, y, and y hat. And you know, verification works because when you pair z with y hat, it just looks like it removes this randomization factor y. Anyway, verification works. This is just the CL19 construction. But when you add in our bases, B1 and B2, those bases are in the public key at the end in verification, the xi hats, but the signer doesn't know these scalars. So when they generate the secret key, the z equals product of mi to the xi, it's going to be independent of those scalars. So the verification actually isn't going to work. So how we solve that is we're going to actually build the messages with these scalars in them. And to do that, we double the size of the messages, and the upper half has the trapdoors and the lower half doesn't. So you sign on the upper half, verify on the lower half, and everything works, except it doesn't. There's actually a recognition attack with this construction, so we have to add even more structure. And this is getting pretty close to the final construction, but it's a little much to explain on stage. Thanks for bearing with me. Just a summary and then a little more explanation, I think. So in this talk, we were able to realize this mercurial signature scheme with the stronger privacy notion. And then in the paper, we constructed DAC. And also in the paper, we add this revocation to our DAC scheme. And basically, the idea of revocation is that we're going to use the recognition attack from CL19 to recognize revoked keys. So we're going to have a revocation authority sign keys from our scheme, and then the revocation authority publishes the secrets of their signatures so that verifiers can iterate through them and check if a key has been revoked. And then because our CRS is so simple, we can just use Schnorr proofs, or discrete log representation proofs to provably update the CRS. And this gives us this serial non-interactive notion of trust. So if someone generates some public parameters, you can update it yourself. And if someone sees the resulting public parameters, they only need to trust one of you, which is nice. And just some more cool challenges that we had and solved in this paper. One of them is that how do we actually make sure that signers are using our bases B1 and B2? Well, we add in these verification bases along with B1 and B2 in the public parameters. And then verifiers can do a pairing over the keys to make sure that it actually is constructed with these bases. And then extending the mercurial signature scheme to multiple levels, which is required for DAC, is actually highly non-trivial. And because you have to correlate all the structure we put in the CRS between the levels. And that's most of the paper, I think. But yeah, it was a really fun paper. Anyway, thank you. Any questions?
Thank you for the nice talk. Do we have any questions from the audience?
I guess from when you describe your construction, now you sign messages that are, I guess, in the exponent instead of as group elements now, or?
Oh, yeah, yeah. I thought someone would notice that. So the little m, you're talking about the little m1? Yeah. So it's normally when you construct mercurial signatures, you don't want to deal with that discrete log at all. But when we're constructing DAC, that message is actually just going to be another public key. So it's going to have, someone's going to know those discrete logs actually. So that's, like you can think of these M1, M2, M3 as just X1, X2, X3 of another key, if that makes sense.
Okay.
Yeah.
Thank you so much for the talk. There was a talk about these mercurial signatures in a prior session where they were distributing the system of signers, like the signers were distributed, whereas in your case it's a centralized, it's a single signer, yes?
Yep.
Do you, well, I'm really speaking from outside, like I'm not really, you know,
Yeah.
it might be a naive question, but like, can you compare the two approaches? Like, what are you effectively dealing with the same problem in two different ways?
I think it's a lot different, actually. And I was thinking about this during Nanri's talk, and I don't really know how to relate them. But I think maybe Nanri can explain it better, or Octavio. Yeah, sorry.
Two really quick questions. Thank you for the talk. First one, do I understand correctly that the attack on the previous CL 19 or 21 only allows the adversary to tell if that's in the same class than they created? So for example, the adversary would not be able to tell if the signature is in different class.
Yeah.
Okay, so it's just like binary. So you can only tell if it's yours or not yours.
Yeah.
Okay.
Yeah.
And the second question is the CRS in the final protocol, the CRS is uniform. So you can just sample that by hashing. It's not like, usually if you say structured, it means you need to do some, you need to generate trapdoor and then discard it. But I think in your case, you can just hash into curve. So it's, you can just hash into curve.
No, you can't. Because, so in this construction, you're right.
Oh yeah.
Like the B1, B2, you can just hash. But when you start fixing correctness, you start mixing the trapdoors. So A3 and A4 have A1 and B1. And then you also need that B1, B2 for the second source group. So I don't think there's any way to use the ROM to sample these. But
Yeah,
okay, yeah.
I understand, thank you.
Yeah, no worries, thank you.
Yeah, if there are no other questions, let's thank Scott again. And there is a lunch break now.